we have our organizer, Anubhab Roy, speaking now. So he probably doesn't need an introduction to this audience. However, as a formality, so Anubhab is an assistant professor at the Department of Applied Mechanics at IIT Madras. And he works on a variety of problems, including hydrodynamic stability, various complex fluids, and geophysical fluids. So over to you, Anubhav.
Thank you, Sumesh. Is my screen visible?
Yes.
Hello, everyone. So today I'll be talking about waves and instabilities in particle-laden flows. My introduction to particle-laden flows happened quite late, towards the end of my postdoc. And very quickly, I realized that the contributions that Bala has made across a wide range of problems, and most importantly, how some of these papers actually are the best introduction one can have when reading the subject. So these are some of the areas which I've been dabbling on since then, primarily in geophysical multiphase flows. Several speakers today and also from yesterday have gone through in detail explaining some of these examples. These are examples from the cloud droplets for warm cumulus clouds, the sundog example that Professor Gozali gave, then Bala's extensive works on turbidity currents, and we have the sea spray that we looked at from Professor Luke Dyke's study. Some of the aspects I've been looking at in particles in turbulence have been related to understanding collisions of droplets. So this actually goes to the case where you're really going down to the scale of cloud droplets and asking the question, what drives their collision and how do they actually become large enough so that they can precipitate and form raindrops? When they're very small, you have condensation driving the mechanism. When they're very large, which is around 50 microns, sedimentation takes over. A key question is, what is the mechanism as it moves forward from this gap? And this is classically known as the condensation coalescence bottleneck. So to this effect, something that I have been looking at in the last few years is trying to understand what is the exact mechanism at the scale of these micron-sized particle that drives the coalescence. Jesse gave a nice talk yesterday talking about the aspect of compressibility. So here, this is an aspect of the non-continuum nature. We are talking about droplets in air. The mean free path is roughly 100 nanometers. So what we showed is that for these cloud droplets, the physics of the continuum approximation breaking down is what drives the collision physics. Since then, we have been looking at exploring the roles of van der Waals forces, and now we are going into the case of particle inertia and attractive electrostatic forces. But today, what I'll be talking about is regarding shallow gravity-driven flows, which are particle-laden. This is a work done by my PhD student Darish, and again, the beauty of speaking now is that I have many who have introduced these examples in the past. Especially, you can see Sung Yong's experiment in the bottom of viscous fingering for particulate thin films. You have these also occurring in the case of granular flows, and also in the context of sediment transport in the bed of the ocean. Now, as you have seen in the first talk yesterday, that for a scenario of this kind, you can classify the system in terms of the different time scales that are there in the problem. You have the viscous relaxation time scale, you have the particle relaxation time scale, you have the flow time scale, and you have a thermal time scale. So taking the ratio of these time scales, you can broadly map this into a parameter space of Stokes, Peclet, and Reynolds number. And you have already been looking at different flow regimes in these parameter space. What I'll be focusing on is a particle-laden interfacial flow and looking at waves in this system. And I'll start off with what is probably not in the geophysical limit, but it's more of a context in the engineering limit, a colloidal film. So the Stokes number is negligible. The Reynolds number is also negligible. So we're thinking of really small particle, micron-sized particle. Brownian motion is something that's to be taken into account. So the first thing to do here, we are looking at the viscosity of the system and the diffusivity being concentration dependent. And the problem we have in mind is the Kapitza instability of a falling film. So for those of you who have not encountered this in the literature, this is just a thin film that is trickling down a surface. So when it rains and you have a glass pane, you would see these nice trickling pattern that happens on the glass window. And if there is a slight slant road, after a downpour, you would see these roll waves that occur on the waterfront. So this is what was observed by Kapitza and his son when they were actually in house arrest actually, in 1949. And Benjamin and E, through linear stability calculation, actually quantified and made a prediction of this instability. What is the threshold Reynolds number at which this film actually becomes unstable? So we had looked at this problem in the presence of particle. And as I said, this is a system where particles are Brownian in nature. So at the preliminary level, the base flow is the exact same Nusselt flow, which is a half parabola velocity profile. And the particle concentration is uniform. So you don't really expect any fundamental difference to the problem other than the fact that the presence of particle would reduce the instability. It's going to act to dampen the instability. And this is exactly what we observe. So the bottom curve, the bottom plot is a neutral stability plot. So this is a plot in the Reynolds number versus wave number of the disturbances done by solving the linear stability equation. So below the curves, you would observe a regime which is actually unstable. And above the curves, outside the curve, you would actually see something that's stable. So the bottom curves are the ones which are unstable due to the surface mode, the one which I just spoke about, the Kapitza instability. And the one that you see on the right side, that's the shear mode, because this is a shear flow down a surface. So it also has the classical shear instability due to the Tolman-Schlichting waves. So that shear mode also gets stabilized. Now, that's fine. So when we move to the particle mode is basically just a diffusion of the passive scalar, the particle behaving like a passive scalar in the Nusselt flow. Now here we see something quite interesting. Everything is damped. The dynamics is not an unstable dynamics, it's a stable damped dynamics. But then based on the value of the Peclet number and the wavelength, you could either see a pure Brownian diffusion, or you could see a transition from Brownian to a Taylor dispersion via an anomalous state. So this is a scenario where you don't necessarily always see the diffusion scaling to be completely molecular in nature, but convection effects can get coupled, and that would become more prominent as the Peclet number starts to increase. Features like this have been seen in the past in problems related to channel flow. Now, this is an example where you would again expect the same thing because you're looking at a problem which is a shear flow. So we go ahead and try to do a nonlinear long wave model of this problem. The problem is particle-laden. So when we write down the evolution equation for the film, it's driven by the flux Q, the volume flux. And when we write down the evolution equation for the particle concentration, you see an evolution that is occurring due to advection, a part that is due to molecular diffusion, but there is an additional diffusion that comes about, that's the Taylor dispersion. In yesterday's talk by Sung-Yong, you had seen aspects of Taylor dispersion in particle spreading occurring when in a Saffman-Taylor kind of an instability. Now, the flux here is due to this falling film. So you can either take an approach which was done initially by Benny for the particle-free problem, where you expand the flow variables in parameter, which is the height of the film by the wavelength. So that's a small parameter in the problem. And you get in a perturbative form an expansion for the flow rate. Now, this exercise is great when you are operating in near Stokesian regime. But when the Reynolds number based on the film thickness tends to become large or order 1, this equation is not the perfect one to use. And in the case when the Reynolds number becomes, let's say, 10 based on the film thickness, you would require to actually solve an evolution equation for the flow rate. So this is something that we have done in this context of looking at the modulation of these nonlinear waves in presence of the particle. So we are solving for the height and the particle field simultaneously using this reduced order model. But this is still a bit unsatisfactory in a sense that we don't really see anything fundamentally different for the instability. Now, experiments which have been done on particle-laden flows with free surface have observed that if the volume fraction is increased, the surface corrugations, which are a proxy or a surrogate for the instability, they tend to become more pronounced. Now, these are particle-laden flows where the Brownian effects are not the most dominant effects. You tend to have athermal effects come into the picture. And again, borrowing on what we have seen yesterday, for a system of this kind, you have effects of shear-induced migration. So particles would tend to accumulate in regions of low shear rate. And if one writes down a continuum model for such a system, there is one popular model, which is the suspension balance model. It captures the aspect of shear-induced migrations, particles' tendency to go towards regions of low shear rate, and also incorporates aspect of particle normal stresses, that the fluid phase is experiencing an anisotropic normal stress due to the presence of the particle. Now, if we take this forward and solve for the development of the film, so we say that there is an inlet plug of particle that's left and it is allowed to flow down the incline and develop. So we do a boundary layer calculation and arrive at a velocity profile that is now modified due to the presence of particle. And most importantly, the particle concentration field is now not uniform. As you can see from the color scheme, that you have a particle-rich layer near the free surface. So the free surface is stress-free. So particles tend to accumulate near the free surface, and you have relatively particle deficit regions near the bottom boundary. Similar boundary layer calculations have been done in the past in the context of granular flows, where you instead use a Bagnard constitutive model. Now, with this base state, which is now an inhomogeneous base state, we previously had a homogeneous base state. With this inhomogeneous base state, if we move ahead and ask the question that what would happen to the instability that we spoke about earlier, would that change? So to understand whether there would be a change, it's a little important to understand why is there an instability in first place. And interestingly, even though the studies have started in 40s, a mechanism for the instability came about sometime in the early 90s. So the free surface, so this is all an example I'm first going to give in the context of particle free, and it carries over for the case of particle. The free surface is a stress-free boundary. The moment we actually perturb the free surface, I would require a compensatory perturbation flow, because now the background velocity profile at the perturbed surface is no longer zero velocity gradient. So I have a compensatory flow which is going to drive the wave down the incline. This is something which we'll get in the long wave limit, the order 1 dynamics that we are looking at, by pushing the wavelength to be infinitely large compared to the thickness of the channel. And if we calculate the wave speed, it is known for the particle free case that the waves are traveling faster than the surface velocity, whatever is the fluid velocity at the surface. Now here you see the Doppler shifted wave speed in the plane of particle Peclet number and the volume fraction, and they still continue to be traveling faster than the fastest moving fluid parcel. If we then move to the next order, which is order K, and this is where the instability comes in, there are two competing mechanisms driving the flow field at this order. So you can think of it's like a flow, which is like a channel flow at this order, where it could either be moving inward towards the crest, or it could be moving towards the trough. So if it is moving towards the crest, then it is a destabilizing mechanism. If it is moving away from the crest, then obviously it's a stabilizing mechanism. Now in the particle free problem, the inertial term, so this is where it's an instability which comes about when you have fluid inertia taken into account. The inertial term drives the instability, whereas the gravity term or the hydrostatic term is the one which is trying to pull out and remove out the ripples. Now, when we include the effect of particle concentration perturbation, we see that this acts also as a destabilizer. besides what was already there, the inertial destabilizer, the fluctuations coming out from the particle is also acting as a destabilizer. So there is a possibility that the presence of particle could enhance the instability. Now, in a different context, completely different problem of a film that is flowing down a heated or a cooled plate, where the viscosity of the fluid is dependent on temperature, it has been observed that heating actually destabilizes the problem, whereas cooling stabilizes it. So if you're heating it, you're basically creating a fluid that becomes more viscous on the top and less viscous at the bottom. Now, why is this relevant for the particle-laden problem? Because in the particle-laden problem, shear-induced migration is naturally giving rise to viscosity stratification. Viscosity stratification is something that automatically comes in because particles don't like to stay in a homogeneous state the moment there is a shear rate in the problem. So particles accumulate near the top surface, which is analogous to what would happen when you have a heated plate problem. So there is another mechanism by which this could become unstable. So going past all the algebra, now just looking at the results that we have, which is inspecting the same neutral stability curves, that whether this, if you look at these curves, if these curves are actually shrinking, that means I have stabilization. If they are expanding, I have destabilization. So Peclet number increasing basically implies that I'm actually having more athermal effects. And here you can see that for a given volume fraction, if I'm increasing the Peclet number, I'm increasing the athermal contribution, I have both the shear mode and the surface mode becoming more unstable. Now, as it always is with many of these stability calculation, it's entirely resting on the model that we have chosen. So how much of this actually depends on the constitutive model? Like if I were to not use a suspension balance model, would I still get this instability? Now, going back to the explanation that I offered, that why this is unstable, that doesn't really require a specific model. As long as the constitutive model has features of shear-induced migration included into it, it would capture the instability. And this is exactly what we do. We have tried this with the diffuse flux model. The diffuse flux model is another approach of modeling suspensions, where the particle normal stresses are not included into the fluid phase, but you have aspects of shear-induced migration included, and the same destabilization due to presence of particle is observed in this scenario. Now, with this, the question is, this was all in the context of particle inertia basically being negligible, the fluid inertia at the scale of the particle also being negligible, and we were looking at order 1 effects of the athermal contribution. Now, going back to my first slide of the geophysical aspect, now if one were to think of these in the context of problems which are more relevant to a geophysical multiphase flow, both the particle inertia as well as the fluid inertia would be order 1. We are talking about sand grains, or we're talking about sediments in a fluid phase. So they would be order 1, and Brownian effects would be negligible. So in such scenarios, and effects of buoyancy also would play into the picture. So we're looking at 3 phases. We're looking at particles, we're looking at the fluid, and we have the interface coupling with air. So in such a scenario, many of these instabilities would have its own manifestations. And just as several things that I have learned reading from papers of Bala, there is a very interesting feature which comes about when you have particulate flows which are negatively buoyant, where the difference in the diffusivity actually gives you a double diffusive instability. Something which people traditionally think of in terms of temperature and salinity comes about in sediment. And so you can have a settling driven and double diffusive instability in sediment transport. So with that, I would like to end my talk. Thank you. Just what we have heard before, repeating what Jesse and Yari said, that Bala is not only known for his scholarship, but mentorship. There's so many things that one has to learn from him. So thank you once again, and very happy birthday.
Okay, thank you, Anubhav. We have time for some questions.
Sumesh, Sangyan has her hands up.
Yeah, please
Hi.
go on. Yeah.
Sorry, very nice talk. Sorry, can you hear me?
Yes,
Yeah,
we can
hi.
hear you. Yeah.
Oh, okay, great. Yeah, I actually have a question regarding if there are more experimental observations where, so because you talked about how the higher viscosity near the free surface can actually be destabilizing, but I can also think of a counter effect where particles, especially with colloidal particles, may be absorbing on the interface and having sort of a stiffening effect. I'm just curious if people have seen that kind of effect of stabilizing effects of particles because of their rise to the interface and potentially absorbing on it.
So yes, that's a very important point. So people have looked at actually Harish, who was there for your yesterday. He has done studies on pulling a plate where they think of the interface getting jammed by particle, and it induces some kind of an elasticity to that interface. So that's a distinct possibility that if the particles accumulate at the interface and it's become sufficiently particle rich, it will behave more like a membrane rather than just like a fluid interface. That's my speculation.
So for your model to be valid, is there a certain concentration regime? Cannot be too dilute, but then cannot be too concentrated?
Cannot be too concentrated, because if the interface gets jammed, then there would be effects that would come into the surface tension itself, which is not included. In the current calculation, the surface tension is always the bare surface tension. It's not being modified by the presence of particle.
All right, well, thank you.
Thank you.
Any other questions for Anubhav?
Anubhav, I have a question. You did not say anything about the buoyancy effect of the particles. Are these, maybe I missed it, are these the ones that you consider are neutrally buoyant?
Yes. Yeah, I should have clarified. These are all neutrally buoyant. Buoyancy effects can be included. In the second part, whatever I spoke about the instability, buoyancy effects can also be included, but we have looked at only neutrally buoyant systems.
Yeah. Well, it's interesting then, the double diffusive stuff that you talked about, in some sense, if you have a buoyancy effect, these particles will start settling down, and then you could create layers of higher concentration, and that will drive Rayleigh-Taylor-like instabilities where they concentrate. And then the competition of that with the viscosity effect that you talk about, it can quickly become very complicated problem. So I wonder whether your analysis can handle that as well.
I mean, I've seen Professor Bertozzi having looked at cases of negatively buoyant particle in these similar scenarios, where she has aspects of shear-induced migration and buoyancy effects both included. But yeah, I mean, that's distinct competition can be there, where they are actually competing against each other.
Yeah, in the context of geophysical gravity current flow, this will certainly be important because the density ratio of the suspended particles to water is about 2.65. So even at modest concentrations, the gravity will start playing a role. Anyway, thank you for a great talk, and thank you for organizing this whole thing. A lot of work for you.
Okay. Anubhav, there is a question in Q&A.
So the question is, can you explain anomalous diffusion? That's a StatMech concept. Do you see a connection? So the StatMech concept, if I understand, is where the MST would grow sublinearly. Here, the difference is, so the growth of MST, if one were to track here, would still be linear. The terminology is often used to differentiate from the molecular diffusion and a case where it's the convection-driven Taylor dispersion. So there is something which is in the intermediate state. So it's a terminology to just make that distinction of the diffusivity. But the MST would still continue to grow in a linear manner. So it would not be the sublinear growth of StatMech.